All right, guys. Number one, what is the difference between the geocentric and the heliocentric model? Talking about solar system setup. Number two, what is the hottest solar layer? The hottest of all the sun layers, matter of fact. Then three, what is the hottest solar outer layer? The hottest outer solar layer, right? If you want to answer in the chat, you can, but otherwise I'll guide you guys through it because I so far don't have my in-person students here yet. Number one, we've got geocentric being the idea that the Earth was at the center of the solar system, right? So geocentric, the Earth was at the center. Humans throughout most of history believe that this was the case. Why? Because, well, they looked up at the sky and they saw the sun moving and they saw the stars moving. That's what they assumed, right? Number two, we're talking about heliocentric. That's the idea that the sun is at the center of the solar system, right? So, again, this is the idea we have now recently and mostly accepted today, right? So again, heliocentric, the sun is at the center. Sun is at the center, right? With that. On page 6 or 7b. So again, evidence has proven that today, given our satellites, telescopes, space stations, we can see now that the heliocentric, just in the past few hundred years, is in fact true. Secondly, guys, what's the hottest of all the Earth layers? Hottest of all the sun's layers is going to be the core, right? Great. Going to be the core of all the layers. The core is the hottest, right? And then of all the layers, right? Which one is going to be the hottest? Which sun layer is going to be the hottest outer layer? Do you remember, Angel, which it would be? Nope, going to be the corona, right? So they're both very hot, but always know the core is the hottest of all the layers. The corona is just the hottest of the outer layers. Again, core is the hottest of all the layers. Corona is just the hottest of the outer layers. Okay. So I'll give you guys a moment for that. We'll move on to our table of contents in a second. Be ready to answer practice questions in the chat. All right. Let's go ahead and move on then to table of contents, which should be the same as yesterday. When my card question is set up, I need you guys ready to answer the practice question in the chat. Answer the question in the chat when it is presented on the screen. Hopefully it should be easy. The answer you can find on page 3B or 4. Answer can be found on page 3B or 4. One moment. All right, so question for today. Which of these solar phenomena are the cause of the northern lights, also known as auroras or aurora borealis? So what causes the auroras? It's on page 3B or 4. Is it A, solar flares, B, solar magnetic fields? Is it going to be C, solar prominence, or D, solar wind? Good job, Angel. Again, what's going to create the auroras? Please answer in the chat. I need your answers in the chat for participation. Thank you, Lakia. Thank you, Joseph. Again, what's going to cause the beautiful auroras in the North and South Pole? What does the sun have that creates this? Thank you, Irina. Got about 10 seconds, guys. Again, this got to get that participation. Make sure. Oh, okay, Lakia, I'll take that. Damiona, thank you, Damiona. Thank you, Sanaya. All right, 5, 4, 3, 2, 1. Anybody final answers? I got Isaac, thank you. Daniela, Diego, appreciate it. Making sure you get the participation. Guys, just so you know, the answer is going to be letter D, guys. Letter D, solar wind. The wind, it goes on the magnetic shield, and that creates the beautiful lights that we see there. I want to give shout outs to Angel, Evelyn, Diego, Sanaya, Irina. Again, great job for those answers. Those were the correct ones. Letter D, it was the solar wind. All right, moving on, guys. Yesterday, we talked a little bit about how planets move, how they orbit the sun, right? and how that was discovered. I'm going to pull this up. So there's no question for this right now, but I want you to think about, again, what was the first thing we discovered that we saw that proved that Earth was no longer in the center of the solar system? It never was. We just assumed that. But what did we see that made us now know that the sun was actually at the center? Okay. If you guys remember, it was the retrograde motion of the planets. Angel, if you remember, if a planet's in retrograde, in what way is it moving? Opposite or backwards, right? So do all planets move at the same speed? No. What planets move faster, the inner planets or the outer planets? Yeah, the closer the planets are to the sun, the faster they orbit, right? Because of the shorter orbit and because there's more what near the sun? More what pull? Yeah, more gravitational pull. So let's kind of, just to get another visualization of it, let's go ahead and get into why planets were doing these loops, and they appear to be moving backwards, not because they're literally moving backwards. It's because their just orbits are the different speeds as ours. Let's take a look. Let's take a look at that, a better visualization of that. Just going to play the first 2 minutes of this, just the first 2 minutes.
Underneath. So let's start with the basic layout of the solar system. The planets closest to the sun move faster and the outer planets move slower, but they all go in the same direction. Apparent retrograde motion is when the planets appear to temporarily change the direction of their orbit. They don't change direction, it just looks that way from Earth. It's an illusion that unfolds over a matter of weeks or months. In this image, Mars was photographed every 5 to 7 days between October 2011 and July 2012. Once all the photos were combined by aligning the stars in the background, it appears as though Mars looped back on itself before continuing on its orbit. A retrograde illusion like this happens when we lap an outer planet like we do with Mars every 2 years, or when an inner planet laps Earth like Mercury does every 4 months or so. But for both Mercury and Venus, the illusion is hard to actually capture, since they're located on Earth's day side, not on our night side. When those planets are visible, it's only right around sunset and sunrise. But assuming you could see it, here's a diagram of how the Mercury retrograde illusion would work. This line shows our view of Mercury against the background stars. As Mercury passes us by, our line of sight shifts so that for about 3 weeks, Mercury will appear to loop back on itself when viewed from Earth. It's simply a function of two objects orbiting in the same direction at different speeds. If you stood on Mercury, you would see Earth make an apparent loop too. I wanted to recreate this illusion on a table.
So again, if Earth was at the center, you would never see planets move backwards like that because they would just be going around the Earth. But because they're going around the sun together, they do these loops like track runners on a track lane. They're going at different loops, right? Different loops. So let's go ahead. I want to continue where we left off from yesterday. Again, I'll check mark everything I want you guys to write down. Don't forget, this is on page 7. So yesterday we finished with this one. We're all good. We did this one already. We talked about Copernicus, who was the first to come up with the idea of the heliocentric model. So let's continue then from that. We have 3 other people I want to talk about, just 2 quick slides. So go ahead. I do want you to write these down. Okay. So Tycho Brahe, again, you've got to know the last name specifically, but just know Danish astronomer who designed, we'll say designed and built. Again, you only write what's underlined. Designed and built very accurate equipment for viewing stars. So he didn't invent the telescope. He just made the best one, right? So he was like, he made the iPhone of telescopes when telescopes were first being invented, were being made, right? So he was the Apple, the Steve Jobs, made the iPhone of the telescopes, right? And then we have Kepler. What did Kepler do? Again, these to be multiple choice questions, guys. Well, Kepler, all right, what was his focus? All right, he demonstrated, as an astronomer, but demonstrated that the planets were not moving and orbiting in circles, but instead they orbited in ovals that we call ellipticals. Okay. So focus on ovals or elliptical. Again, an elliptical is like kind of a round oval. It's like a hybrid of a circle and an oval, or to some degree. And it kind of changes over time sometimes. So again, planets orbit in ovals called ellipticals, not in circles. That's Kepler. Brahe, he was the guy that made the best telescope. Okay? That was his idea. All right. So let's go. I want to show a quick video clip when my in-person students are ready of that elliptical movement. And again, this idea was from Kepler. Do not forget that. Do not forget. Again, this stuff should be on page 7, guys. Page 7 from yesterday where we left off. Okay. So real quick, here's how planets orbit in ellipticals. Again, going to keep the lesson quick today, guys. We're almost done here. We got one more thing to look at, and I want to play a little review game, and then we're done. Okay. So as you can see here, okay. Again, notice how is the sun in the center? No, it's a little off, right? So the sun's usually going to sit slightly to the right or slightly to the left. Also notice, how does the planet change its orbit as it gets closer to the star? It gets faster when it gets closer, right? That is normal. That's what it does because there's more what near the star? Gravitational pull, right? So see, this goes up and speeds out around. Okay? And again, that was discovered by Kepler. Let's do our last person of the day. One more. Again, like I said, keeping things short today. We are going to go ahead and look, and here's like those ellipticals, right? Except the sun should kind of be to the right or the left. Galileo, last person, Galileo Galilei. Okay. And we'll just say this. Use the telescope. Use the best telescope, right? Brahe's telescope. To verify the predictions of the heliocentric theory. Sorry about that, guys. My bad. That was the mouse pad messing up. Okay, my mouse on my laptop. Okay, so he, again, didn't invent the telescope. He just made a lot of discoveries and was one of the first big people to support the heliocentric model. You got to remember, you had Plato, a lot of Greek genius philosophers supporting the geocentric model. He was one of the first big-time genius names to support the heliocentric model. And he loved the telescope, was a big fan of it, right? Really used it a lot. So those are the 4 names you need to know. Know the names, the last names of what they did. Let's do our last card question of the day. Feel confident that you guys will know it. I feel confident you guys will know it. All right, let's take a look. That is it for notes. Oh, I got one more activity, guys, real quick. One more activity. But let's take a look at one more like little note activity. I forgot. All right, our last card question of the day. Okay. Which astronomy figure came up with the heliocentric model? Again, which astronomy figure came up with the heliocentric model? Got to know the names of what they did. Like I said, is it A, Galileo, B, Brahe, C, Kepler, or D, Copernicus? Again, he didn't support it. He was the one who came up with it. He was the first person to claim this idea. See what you got. See what you got. Answer in the chat, guys. Answer in the chat. Great job, Angel. Great job. Thank you. Let's see. Joseph, Diego, thank you. Again, he was the first to come up with the idea. Isaac, thank you. Sanaya, thank you. Lakia, thank you. Yorkies, thank you. Got 10 seconds. Evelyn, thank you. Irina, great. 5 seconds, guys. 5 seconds. Participation, guys. Make sure you answer. 3, 2, 1, 0. Guys, the answer to who came up with the idea first is going to be Copernicus, letter D, Copernicus. I want to give shout outs to Angel, Irina, Evelyn, Sanaya, Diego, Joseph. I think I said, yeah. So great job for getting that right. Great job. Great job. Okay. Last activity before we do our review game. I want you guys to go ahead, make a T-chart on page 6 or 7B. Make it like 1/3 of the page, make a T-chart. We went over law versus theory in the fall back in August. Oh, and then Angel, make sure to get this down as well. Yep, T-chart. 6 or 7B. But we do have to go over it again for this semester. But we haven't seen it in like 8 months. So we're going to, instead of doing the whole notes about it, the whole lesson I had about it, I'll take up the whole class, we're going to do a 5-minute breakdown T-chart activity for this, make it a whole lot easier for all of us. On the left side, make law. On the right side, make that theory. Okay. If you recall, Angel, are laws better than theories? A good idea, right? A lot of people say they are, but no, they're actually just different. Can theories become laws? Good idea, again, which most people assume, but no, theories and laws can't become one another, and laws are not better than theories. So that's why I want to break this down, because a lot of us have an assumption that one's better than the other. That you can that theory can become a law, right? So we're gonna watch a little video. It's 2 to 3 minutes. A little cartoon. It's gonna break down the differences. We're gonna bullet those down, write those in bullets for our potential next notebook check or quiz, or online test, right? Okay, so let's break down the differences between law versus theory.
Chat with a friend about an established scientific theory, and she might reply, well, that's just a theory. But a conversation about an established scientific law rarely ends with, well, that's just a law. Why is that? What is the difference between a theory and a law? And is one better? Scientific laws and theories have different jobs to do. A scientific law predicts the results of certain initial conditions. It might predict your unborn child's possible hair colors, or how far a baseball travels when launched at a certain angle. In contrast, a theory tries to provide the most logical explanation about why things happen as they do. A theory might invoke dominant and recessive genes to explain how brown-haired parents ended up with a red-headed child, or use gravity to shed light on the parabolic trajectory of a baseball. In simplest terms, a law predicts what happens, while a theory proposes why. A theory will never grow up into a law, though the development of one often triggers progress on the other. In the 17th century, Johannes Kepler theorized cosmic musical harmonies to explain the nature of planetary orbits. He developed 3 brilliant laws of planetary motion while he was studying decades of precise astronomical data in an effort to find support for his theory. While his 3 laws are still in use today, gravity replaced his theory of harmonics to explain the planet's motions. How did Kepler get part of it wrong? Well, we weren't handed a universal instruction manual. Instead, we continually propose, challenge, revise, or even replace our scientific ideas as a work in progress. Laws usually resist change, since they wouldn't have been adopted if they didn't fit the data, though we occasionally revise laws in the face of new, unexpected information. A theory's acceptance, however, is often gladiatorial. Multiple theories may compete to supply the best explanation of a new scientific discovery. Upon further research, scientists tend to favor the theory that can explain most of the data, though there may still be gaps in our understanding. Scientists also like when a new theory successfully predicts previously unobserved phenomena, like when Dmitri Mendeleev's theory about the periodic
I'm going to
table
go ahead and stop it
predicted
there.
several
Because it broke down basically the main points I wanted. The rest of it kind of goes off a tangent about other things. But so law and theories, is one better than the other? No, one's not better, right? They just have different jobs. So what's the job of a law?
To predict the results, what happens, and to resist change.
Yeah, absolutely. So laws are going to, my bad, predict results. Theories are going to do what? Explain, right? So laws, again, predicting results. Theory is an explanation, right? So they have different jobs for different topics in science, right? And law is going to ask what, a theory is going to be why or how, right? So like law is like the person who just says one word or doesn't say much and just gives it to you very direct and doesn't say too much. Theory is like the person that's going to describe and explain and tell you a story, right? Talks a lot. Okay, and then lastly, also don't forget we've got laws don't change, theories do change. Whatever wasn't mentioned in the video, please add that as well. Again, this is on page 6 or 7b. Laws are just statements based on phenomena in nature. Okay, theories are explanations. Remember, explanation, it's you say a lot more, you're telling a story from observation and experiments. So again, they're both tested. They both have a lot of data and a lot of evidence and support. They just are kind of different in their style and different in their, different in their style and different in the way they go about things, right? Okay. Laws are more math-based. So anything in science that's more of like a math equation, like chemistry, physical science, that's going to be laws. Okay. Theory is more like biology stuff, like concepts. So things you have to describe that you can't put in a math equation. Angel, do you have any, do you know, let me see, I think someone's in the chat. Do you know any examples of laws? Oh, okay. Isaac, we'll be done before that time. No worry. We'll be done before that time. No worries, Isaac. Thank you. So what are some examples of laws in nature? What's this? When I drop something, what brings it down? Gravity, right? So anything that I can calculate with an equation, that's going to be a law. So just put for examples, motion, thermodynamics, and gravity. And then what are some examples, or what's an example of a theory? I said it. So what's a popular TV show? The big what theory? Yeah, Big Bang Theory, evolution, cell, atomic theory. So anything that has to be described to understand, that's a theory. Anything that is more math-based, that's going to be a law. Again, they're just different. It's oranges to apples. Make sure, again, that's it for the T-chart, guys. Take a picture of that. We have one more activity for today, then we're all done. Have your phones ready for a little Kahoot review game. Do your best. If you can't sign in, let me know because you're on your phone already on the Kahoot. Follow along the best you can. There's 15 questions. A lot of them could likely be used on your online test, so do participate. My top 3 or 5 will get double, triple bonus for getting their stuff done, and everybody will get that signs in will get the 2% bonus for the 4th quarter grade. Okay. All right, let's go to the last activity, then we're all done for the day, guys. 15 question practice Kahoot review. Do your best. And I think Daniela, or let's see, Lakia. Okay, thank you for the heads up, Lakia. Again, follow along the best you can, because like I said, guys, you might likely see these again on the online test coming up here soon. You guys go ahead, sign in. The number is 710